In my view, this is the most exciting part of Haskell. And this session consists of 2 talks. Oh, I'm Yukio Shikame from University of Tsukuba, and this session has 2 talks. And the first talk is by these guys. And Pablo will be given a talk about the KeyMonads. So please, you have 20 minutes.
Can anyone hear me? Okay. All right. So I'm here to tell you about something called the KeyMonad and its applications to dynamic typing in Haskell. So this is joint work with Atze and Kuhn from Chalmers. So what is a KeyMonad? We introduced 2 type constructors, key and keyM, with that kind, and an operation called newKey, which is a monadic operation in the KeyM type, which is going to be a monad, and has no arguments and returns something of type key. And key has 2 arguments, S and A. And we're going to get into S in a minute, but A is basically the type of that key. The idea is that keys represent some unique name that we can use in our program. So it's a unique, fresh typed name that we can create with this operation. And then there's another operation called test equality that takes 2 of these keys, potentially with different types, but the same S, and returns maybe a proof that the types are the same. And we're going to talk about that in a moment as well. And we have another operation called runKeyM, which takes a key computation and basically executes it. So makes all the fresh keys that it wants to make, performs all the quality tests that it wants to make, and just returns the final value. And KeyM, yes, sorry, there's an S missing, yes, sorry. Yeah, so KeyM should also have an S, yes. And this is a monad, so yeah, KeyM of S has an instance of monad. And as I've said, these are unique names. Note that there is no KeyM in the type of test equality, so the test is actually pure. And in the type of runKeyM, you'll see something that looks like the trick in the ST monad. So the computation itself is polymorphic on this S to make sure that the keys produced by the computation can't escape their scope. And that's basically what S does. We call that a scope type variable. And because of its position, it's existentially quantified. And, well, as we'll see in the rest of the talk, it's kind of hard to really prove what that S means, or to have an intuition of what that S means and what it does. Yeah, so let's look at test equality in more detail. So this is the type that test equality returns. It's basically the type, it's a GADT that encodes propositional equality. So we have a REFL constructor that gives us evidence that two types unify. And note that the semantics of test equality is supposed to be as follows. If we give it 2 keys, it will return either just REFL or nothing. It returns just REFL if the keys are the same and nothing otherwise. And additionally, because of this REFL, I mean, we can match on this, and we get a proof that the types of the keys are the same. Note that this is not equivalent to just runtime type equality. When test equality returns just REFL, it really means that the keys are identical, not just that the types are the same. So they have to be exactly the same key. So this is basically the KeyMonad. And now we can think of what can we do with this monad? Why is it useful? So the first thing we're going to look at is we call it unconstrained dynamic typing. The idea is that we can have some form of dynamics in Haskell using these keys as follows. We can make a type called box. The idea is that if we have a key, we can use it to lock a value into a box and hide its type. So we can have this constructor lock, takes a key, and something of type A, and returns a box of type S. So the idea is that these boxes are also restricted to one key M computation, one context. And then we can unlock these boxes. If we have the original key that we used to lock it in the first place, we can unlock them. Basically, we do a pattern match, take the K prime, and then do test equality on the two keys in scope. If we get just REFL, then we can return the X that is in the box. So this type box S is essentially like dynamic. And the difference is that we can do this without typable constraints, and that's where the unconstrained comes from. So yeah, this is one possible application. Building on that, we can also have heterogeneous maps. So something we call a key map of S is basically a list of these boxes. Since each box associates a key to a value, we can think of this as some kind of mapping from keys to values, but where the types don't need to be the same. And actually, I would say this is the main application, because all the other applications we're going to see in the rest of the talk somehow use this key map behind the scenes. So this is the main thing we can do. So one of the things we can do with this key map is the ST-monad. It's a particularly inefficient implementation of the ST-monad, but it's still, it's about expressivity. So an ST-ref can be represented by a key. The ST-monad itself is just a state transformer where we keep this key map that basically stores the values of all the references in the scope. And we can implement new ST-ref and write ST-ref and read ST-ref in a fairly intuitive way. I don't really have much time to go into, but yeah, it's just inserting things into the key map or looking them up in the key map and so on. So that's one thing. What else can we do? Well, when we implement a lambda calculus, we might need to represent, we might be interested in a way of representing terms and variables in our implementation language. And this is an example of a type that represents lambda terms. So we have var, so we have a type of names, which is ints, and we have variables, lambda abstractions, and applications. However, there's something quite wrong with this type, because it's not very useful. If we want to use this in an implementation, we might want to have an environment, right, for an interpreter, but how will we represent it? We need some kind of heterogeneous map, essentially. So you sort of see this coming, I guess, but yeah, we can represent lambda expressions using keys as names. Then yeah, we have kvar, which instead of a name takes a key, and lambda expression, and which takes a key, and applications are basically the same. And in this context, we can represent environments with key maps, and we can write our interpreter. We can even think of well-scoped representations of syntax. So this is an example of parametric higher-order syntax, where we have a type V of variables, and yes, this V should be variables, and we can encode our abstractions using the host language abstraction. So we see in the second constructor, plam, the first argument is a Haskell function that takes a variable and returns a parametric COAS term. So yeah, in this context, we know, so this is well known, of course, and we know that terms, when we close over that, terms of that type are always well scoped. So this is sort of a convenient way of having guarantees about well scoped terms. And there's another way in which we can do well scoped representations, which is using typed De Bruijn terms. And this representation is actually, well, doesn't have any function spaces in it, but it has some complicated types. So the idea is that the first argument to this data type, that T, is a type level list that represents the types of the variables in scope, or the free variables of a term. So a variable is introduced by giving an index into this list of types, this type level list. And when we introduce an abstraction, we extend that list with a cons. We add the new variable. Applications are still kind of similar. So yeah, that's what I said. And we know that terms of type Brown empty list A are also always well scoped. So these are two ways of getting guarantees in our implementation language about the terms that the terms of the language that we're implementing. So how do we translate between these representations? Or why might we want to translate between these representations? The idea is that for us, the parametric higher order syntax representation is nice and abstract and is kind of nicer to work with, but the Brown representation, since it doesn't use any special terms in the host language, is easier to work with in terms of the implementation or doing optimizations. There are some examples of work where we can use these de Bruijn terms, type de Bruijn terms to compile lambda terms into hardware. So there are lots of interesting applications of these things, and it might be useful to translate between them. So again, I don't have much time, but you can read the paper for the details. We basically implement that kind of translation between these two types. And the meat of that translation is, again, a key map in some way. Another thing we can do with the KeyMonad is to embed arrow notation into Haskell. So this is an example of two arrows, F and G. They go from some type A to integers. And let's say we want to compose them in this way. So the first step is to duplicate the argument, and then we apply some F to the first element of the pair, then apply some G to the second part of the pair, and then we add up the results and we get an integer. So that's a straightforward composition. And we normally write that, or we have the option of writing that using proc notation or arrow notation in Haskell in that way. So let me just, yeah, so this Z is the argument, and here we see that we feed this Z through F and G to get X and Y, and then we add them together and return that. So this is considered slightly nicer to write than the equivalent point-free version of this expression, sometimes by some people. And anyway, but this is, but this is built in, or needs a compiler modification, and we show in the paper that we can also embed this, well, something that looks very much like this syntax using the KeyMonad. And the idea is we get, again, the details are very hairy, but we get a monad over here, which we call arrow syntax, but it's essentially a crippled monad in the sense that it basically removes the extra power that monads have and arrows don't have. And we have some fancy definitions for these operators over here so that everything works out. And to be honest, it's a bit of a gimmick because this part, we need to use applicative syntax to express this operation. And this is because the way we define these variables are no longer of the same type here, so it gets complicated. I really don't have 7 minutes. So, but yeah, you can read the details in the paper as well. It's still something nice to have. So, how do we implement the KeyMonad? There are many ways of doing this, but the one I'm going to show right now is using a splittable name supply, which we call NS. And the idea is that the key-m computation is isomorphic to a reader monad where the environment is this name supply. And the keys themselves are the names that we can get from the supply. And the implementation actually uses unsafe features, pretty much like SD does. There are other ways of doing this. So we can also use, for example, a state monad with some kind of globally unique names and so on. And there are fancier implementations in the paper as well. The name supply is basically a path in tree. And you've probably seen this before. This just, we can represent either start or left or right. So this is, if you have something like left, right, start, this means the left child of the right child of the root. It just represents a name, and the idea is that we can split it by just taking either the left part or the right part. So new key is just using the function that takes the first name from the name supply. Bind splits the name supply in the way you might expect, so giving one name supply to each branch or to each part of the tree. And then we can test these things for equality, and here comes the unsafe part, of course. So we look at the names, T and R. If they're the same, then we just unsafe coerce REFL. So, yes. So now comes the question, why is this safe? Or the question of, is this safe? And this is a very important question, of course. So I guess another way of thinking of this paper is the claim that this unsafe coerce is safe to use at this point. So what do we mean by safety of the key monad? We identified three key properties. Type safety, which is essentially saying, you can't prove that two types are the same if they're not actually the same. Referential transparency, so keeping an essential feature of the language, which is that expressions always evaluate to the same result in any context. And abstraction safety, which is basically parametricity. And it's something that is sometimes used to justify why the ST monad is safe, and what the S in the type of run ST does. So these are the things that we're interested in. We tried to prove these things, but we failed. But yeah, I guess my point is it's very hard to prove these things. And actually, the ST monad is also lacking in these proofs. There have been several attempts to do this, but there were technical problems. And so we looked at lots of papers, and we didn't find any convincing argument that this is the case, especially not all three properties. But there is some intuition as to why this is safe. So let's take a random key M computation here. That's the M. And let's say it makes two keys, type A and B. So when we look at a key, so let's say that K is of type key SA, we can see that intuitively the type A is uniquely determined by two things: the value of the key itself and the S, meaning the scope type variable that it has. Yeah. So the K is unique because of the way we've defined our key M computation. So in the implementation I showed, is a name supply, and we know that we're splitting the name supply upon every bind, and whenever we create a new key, we're getting a fresh one out of the name supply. So it's because of properties of the name supply, we know that those keys are unique within the same key M computation. And then if we have another computation, it will have some, intuitively, it will be some S prime, because it will be some other Skolem variable. And we know that these S's are unique because of the way the type checker works. So we can give sort of an operational interpretation of that in terms of how type checking happens. Many times, people invoke parametricity for this. But the problem with doing that is that after adding these features, we no longer know if there is a parametricity theorem for our calculus. So if we take system F, for example, and we add the KeyMonad, how do we know that this has a notion of parametricity? This also needs to be proved. So yeah, this is our intuition. We tried to do this to prove something along these lines, but failed. I guess maybe one of the reasons why this failed is that there's kind of an interplay between something that happens at runtime, which is how the keys are generated in one computation, and something that happens at compile time, so the types. And that's why parametricity would be sort of an important stepping stone in proving something like this. So I'm going to summarize. So I've seen the we've seen the KeyMonad. It includes fresh type names with pure equality test. That's sort of a one-sentence summary. We've seen some applications, and we've seen that there's kind of an elusive proof of safety, much like the ST monad. And this is a call to arms that we actually need to prove the ST monad correct, because we're still using it. And since the KeyMonad is simpler, we think that this would be an interesting avenue to achieve that. Thank you.
Questions? Any questions? So he raised a lot of open problems and so. Any comments? Oh yes, sorry. Yeah.
Hi. Are you familiar with the new type rep stuff that's going into GHC at the moment? It's sort of a new formulation of typable and an indexed form of type rep.
No, I'm not sure I'm familiar with that, no.
Okay. We had there was a paper at the Wadler Fest earlier this year on it.
Oh,
and
right.
I'd be curious for a comparison between that
Right.
and this, because I think it achieves a lot of the same it's sort of working in the same direction. It doesn't take a monadic approach, but I guess we could take that offline.
Yeah, sure. Yeah, we should talk about it.
Any other questions? We have 3, 4. Oh yes. Yeah.
I guess I just was curious as to if you can give any more details about what you tried to prove and why, what sort of obstacles you hit.
Yeah, so we tried to prove type safety. We built a little, like system F with the KeyMonad, sort of with that interface that I showed in the first slide. And we tried to give a sort of a parametricity theorem for that. And I think sort of the stumbling block was the relational interpretation of keys, because there wasn't much to go on sort of to establish that.
You're jumping straight in with parametricity. I mean, because you said, like, it seems like you don't necessarily need the full power of parametricity. You just need the fact that the key and your S parameter uniquely determine the type.
Yeah. So I mean,
so could you is that on its own easier to prove, and then following on?
I think it's hard to come up with a model where you can sort of prove this without using any meta-level reasoning or things like that. Like, this intuition, I guess it seems to make sense, but there's lots of moving parts. And yeah, what we did ended up being something like, because of the way the typing works, then we can assume that all these things are separate. But I mean, it might be convincing to some people, but we don't think it's a proof, because it's sort of, that's precisely what we want to prove. Like, why are they separate?
So something like this is a reasonably standard technique in ML systems.
I don't. Oh, yeah. Sorry.
Something like this is a reasonably standard technique in ML systems, because you can encode something very like the key setup using ML's exception type.
Okay.
So it's kind of different than this because you can't separate different uses of names. It doesn't use a monadic style. There's just a single global name supply. But that might be somewhere to look for techniques on how to prove type safety. There is a type safety result for standard ML, and including generativity. So this sort of issue might be solvable using the same techniques.
Right. Well, yeah. If sure, if it can be expressed with that, sure. Yeah. Thanks.
Is it possible for key to be kind polymorphic in A?
I don't see who's speaking. Sorry.
Is it possible for key to be kind polymorphic in A?
No. Because of the type of because of the type of keys. I have to go back to the end. Yeah. So this is like for all A in the usual sense. So it needs to be star.
I'm sorry, for all, but where is the for all?
The type of new key has a. It's not written, but it's for all A.
Yeah, but you could make a new key also kind polymorphic, right?
Sorry?
You could make a new key for all A of kind star.
Yes.
Of kind K.
Well, yeah, we could write that, but that's not what we wrote. Yeah. I mean, are you asking for possibility? I don't know. I don't know what that would even mean in many applications. I mean, we had trouble proving that with star. So I mean, I guess having a K there would be hard.
And you're only using the last index as a arbitrary name for stuff. There's no reason it has to live in star. You're not actually using it as a type. So, I mean, you can change the kind there, and as long as you sort of stash it in your key M, who cares? Have a key proxy.
Yeah.
That's what key proxy is there for.
Yeah. I guess you could have it.
That's what we do with Macro, and I mean, we haven't proved correctness just like the other, but yeah, I don't see why it can't be.
But yeah, I'm not saying it can't be. I don't know how.
So Sam, last question.
Okay, so my question was essentially the same as Stephen's actually, but I was just wondering whether you looked at models of dynamic state creation elsewhere, so like ML style references, which people have studied.
Right.
Have you compared your work with that at all? Because that might give some hints as to how you might prove these things.
Okay.
Seems very related, and it's a very difficult problem.
Mm-hmm. Okay.
Yeah, let's thank the speaker again.
Thank you.